Are the answers to the warm-up correct?
9x.
Please double check quickly. There's a smiley face. Extra points for that. Notice here, first of all, you're welcome for a warm-up that doesn't feel anything like what we were doing last night. You're welcome. Second of all, these are important for what we're going to do today, I promise. Third of all, notice that there could be as many as 2 answers to these particular style of questions. In fact, for all of these, there are 2 answers on these particular problems. Do you like them? Did you get them all right? Let's move on. Okay. Today's goal, we're changing gears maybe a little bit, is to solve some equations. We haven't actually done that recently, so I think that's worth talking about. So I have the following prompt as kind of the stem of this question. Says, prove or disprove the following statement. I think that's a good way to open today's lesson because we've just been talking about identities. And by identity, we mean a statement that is true for all x values, right? So for example, apparently, this expression, as nasty as it is, and this expression have the same value. If you plug in an x value to both of them, you get the same result if you plug it in here or here, right? So that's what we mean by an identity. Regardless of the x value you choose, this is equal to this. So my question is that true here too? Is this true for every x value? That's the claim. If someone claims this is an identity, that's their claim, is that this is true for every x value. Now, what would it take to disprove that? We've already felt like what it would feel like to prove something. What would you have to do? Yeah, you need something called a counterexample. So can you provide one? Anyone just stare at it for a few minutes, try a few x values? If it indeed is not an identity, then it should be pretty easy to find a counterexample because like finding something that does work should be the lucky thing. You find one that doesn't work?
If you do pi root 2.
X equals pi root 2. Plug it in. Everybody check on it. On the left you get, and on the right you get. Is pi root 2 something that demonstrates the falsity of this statement? The universal truth of this statement has just been blown out of the water. If you plug pi root 2 in the left, you get what?
0.
You guys see that? You get 0 on the left, but if you plug pi root 2 in the right, you get 1. But something not 0, true. Okay, so the point is it doesn't work though. So we've just disproved it's definitely not an identity. But then we could ask, just for fun, we could also ask the question, so when is it true? And that amounts to doing the thing you've done like all your life, solving an equation, right? So now let's treat it as we normally would in a conditional equation and actually solve it. Okay. In fact, I gave a problem like that to my Algebra 2 kids the other day. I had a couple students who made the following mistake. They were like doing high order polynomials like this, and they said x cubed minus x squared, and they simplified that, and they said, oh, that's x, right? None of you would make that mistake, right? But I asked them to evaluate whether that was true or not for all x. And it was very quick for them to come up with a counterexample too, because basically any number you picked would provide a counterexample. Like 3 they picked, and it didn't work. Oh, okay. They picked another number, it didn't work. It seems like it never worked. But it's still an interesting question to follow up with by saying, okay, well, for what numbers does it work? 0, clearly, works. And maybe you can find 2 other ones that do work, you know? Like maybe there are times, coincidentally, where it does work. Anyway, so same thing here. I'd like to do the same kind of thing. How would you proceed now? If we just were to do this as a conditional equation, you're allowed to work across the equals now. We're gonna move forward on the condition that it's true, okay? And we're gonna find the x values for which it's true. Let me ask you this: how would you solve this equation? X squared equals x. Divide by x. Except what happened? Just be careful. Why is dividing by x maybe not a... Yeah, you're missing a solution, right? So you should be a little careful. What would you do instead here when you're solving this equation? How do we avoid that issue? I think if you divide by negative x, you'll get the same thing. You'll get negative x equals negative 1, and you'll get x equals 1 only. How do we avoid missing the solution? The other clear solution is x equals 0. Why are we missing that? Yeah. What was the first thing you said? Sorry. Subtract x and then do what? Factor is the word. So, talk to me about how to do this one again. Subtract. Yeah, how about we do the same thing here? And then factor it. To the extent possible. And then, I mean, I don't know, I don't have too much more to say. Now, okay, we just, now it's clear that either sign needs to be 0, which you would have missed if you hadn't, you would have just had this equation. So you're going to miss these solutions. All right, so if sine is 0, we'll solve that. Or it could be true that 2 cosine x minus 1 is 0, right? Either one of those would definitely make this equation true if either one of those statements holds. So over here we get x equals on this interval, what values? 0 or pi. Do you understand now why we did the warm-up, by the way? The warm-up will be like the field of every one of these problems at the end, okay? You'll have like little mini warm-up problems to do all throughout this at the end of a bigger solving problem. Over here we have cosine x is a half. When's that true? Katie, you want to answer that one?
No.
Why don't you just ask Siri or something?
I left my water bottle in fridge. I'm texting my friends.
Oh,
so I
okay.
can get it.
Oh, I wasn't calling you out on your phone or anything.
Good.
You were using your phone. I didn't even know that. I think. What is the answer? Sorry, got distracted. What did you say? 5 pi or what? 5 or 3, and 5 pi or 3. So you could confirm this graphically too. You could graph this in y1 and this in y2 on the interval 0 to 2 pi. You'd see 4 intersections. They'd be at these places, right? Or you could, if you graph this in y1 and look for zeros, you'd find 4 zeros in these places. Something like Yes, of course. Yeah, these are non-calculated questions for the most part. So are we having fun yet? Is this good? Does it sound like this is going to be fun tonight? Okay. I will go back for 1 second. Is that good? Yes? Okay. All right, let's do another one. Yay, because it was so much fun on the first round. Here we go. I'm always looking for a first step. There are actually many ways to do these problems. So, Gabe, do you have a suggestion? Beta equals what? So he's multiplying both sides by cosine beta. Okay. Okay, I think I'll go with that. I like that. That is actually not, well, it wasn't my first thought, but I think it's going to work great. So let's do it. Actually, it makes for a nice looking equation, actually. I kind of like it. And then, Jasper, what do you want to do? I think I get it. I think I see where we're going with this. Do you? So we get sine beta times sine squared beta minus 1. Okay, I'm with you. So sine beta is 0, or we get sine squared beta is 1. We already solved this problem. We get 0 or pi. Over here, what's going on there? So sine squared beta is, remember, sine of beta, all squared is what that means. So how would you proceed here? Yes, that's true too. What does sine beta equal? Yeah, 1 or -1 Or say what you said, Cassie, too.
You could factor the difference between the squares of the equation and then.
Yeah, you could have factored this one more step further and also gotten these same results that either sine beta is 1 or sine beta is negative 1. Good. We still need to say what beta is here. What's beta? Yeah, when is sine 1 or when is sine negative 1? At the things you just said. Good. And then we're done with this problem. Oh, wait. Let's see. Let's make sure. I wouldn't have just given you another example. What would I have for practice? It's got to also teach us a lesson of some kind. There's got to be another little snag here, doesn't there? Look for the snag and come back to me in a second. I think these make the original equation undefined. Check them. You see? Yes? So cosine of pi over 2 or 3 pi over 2 is 0. That's a problem. Also tangent, too, is undefined at pi over 2 and 3 pi over 2. So in fact, it makes both sides undefined at those places. The only solutions are these two on this interval, 0 and pi. Right? So there had to be a snag, right? There had to be another lesson for us there. I hope there's another snag on this problem. That'd be cool. All right, but let's proceed solving this in whatever way you like. Give me a first insight. Again, there are lots of good ways to start this problem, I think. So I'll take a suggestion when you have one. What do you want to do? You look excited about this, Christopher. Sure, I'll go with you on that. So that gives us 2. My board is not being very good to me right now. Oh. 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 Yeah, do that. And we'll come back together in a minute here. Let me see if my board is not working for me right now. All right. Ignore all this scrawl. Here we go. It's all over here. So what do we get over here? Cosine y times tan y is sine y. Okay, good. And then Jasper, what are you gonna do next?
Wait, how do you
It's not like I have a point to make or anything, or a horse to beat. But thought I'd keep bothering you. All right, and then yeah, again, this is not maybe the interesting part here. Sine y, 2 cosine y minus 1 equals 0. So sine y, I feel like I've solved this problem 1,000 times, equals 0 implies that y is equal to 0 or pi. And over here we get cosine y. I think we solved this one before too. Equals 1/2 implies that y is what, pi over 3 and 5 pi over 3 again. Check those, please, in the original equation. Again, we have this kind of snag issue that we just learned about, that we might have extraneous solutions. In fact, it's very often true that we'll have extraneous solutions in these equations because of just the nature of these trig functions, right? There's lots of places where they can be defined. And just be real careful about that. Do all of them work, though, here, or check? Well, tell me, Ben. 0 and pi, I think, failed, right? Right? So, good. So pi over 3 or 5 pi over 3 are the answers. Except, hold up, there is one more snag for us on this one. And that's the instructions. This time the instructions have something for us that we didn't know this. And it says for all y. Now, there are an infinite number of solutions. I hope you can appreciate that with these trig functions, unlike other equations you solved in your life. There are more than 2 solutions. There are an infinite number of them. So how can we even begin to write them all down? Bryn is here to help. Go ahead. Oh no, you're not going to help? Okay. She had her hand up. She has a suggestion. Go ahead.
Write it as y equals inverse cosine of 1.
No, let's write it as pi over 3 and 5 pi over 3. Oh, I see what you're saying. How do you write the solution out or something?
Yeah, like if you wanted to get all of
Well, I think we can start. Let's start naming the other ones. What's another solution that we didn't list? 7 pi over 3. Yes? Let's go terminal with this. Pi over 3. 11 pi over 3. Negative pi over 3. Yeah, right? So Lauren has some help for us. Yeah, I feel like we maybe have talked about this before, but pi over 3 plus 2 pi n, where n is any integer, right? It's anything coterminal to pi over 3, right? I feel like we did that early on in our discussion of back in unit, whatever. Michelle, you don't want to miss this. This is like golden stuff right here. This is beautiful. Katie will tell you. She looked down for a minute and then amazing things happen. She missed so much.
I'm so glad I came back.
Just yeah.
I'm saved.
Give some testimony, okay. And we can do the same thing here. We might want to specify also by n we mean some integer n. Any integer. So let n take on every value along all the integers, positive and negative integers here we're talking about. And you'll be generating, if you let n be all the integers, you'll be generating all the solutions. Yes? If n is like negative 17, you'll get a solution, right? Does that make sense, Piper? Okay. Keep her accountable. Okay. There is actually a bonus points for style available here. There's some style points available. Another really slick way to write the solutions would be this. Can you see why? You can just write it that way.
Oh, that's what I was thinking of.
Right? Do you see why? That means this angle and everything coterminal to it, but also this angle, negative pi over 3, and everything coterminal to it. So full credit for either box, but yeah.
What's that thing at the bottom?
That's a capital Z, which means the integers, right?
But I thought he was asking if this squiggly.
Oh, that means is a member of.
No, the other squiggly.
Oh, that is my board malfunctioning. Moving smartly along. Let's keep going. Got things to do.
Find all values. Is this different from?
No, it's not different than the last instruction. It's still solve for all values of u that would work. I'll do the first step for you. You're welcome. Why is it that we keep solving sine u equals 0? I don't know. I think I wasn't very creative in coming up with these problems. That's why. Okay. So you get 0 and pi. We've done that a lot of times. Oh, this is an interesting one that we haven't talked about recently. When's tan 1? Someone help me out with that one. Pi over 4, and you got to put that away, Piper. You got to put that away? Right. And I thought it was started before. All right. And what else? 5 pi over 4, and an infinite number of other things too, right? But we'll write those down just to humor ourselves for the time being, at least, just to get our heads going. But because, like I said, those are just on the interval 0 to 2 pi. You want to say some other ones though? How can we write that? I mean, certainly one way to write it would be to do the same thing we did before. U equals 0 plus 2 pi n. U equals pi plus 2 pi n. Or pi over 4 plus 2 pi n. Full credit for this. Or 5 pi over 4 plus 2 pi n, where n is an integer. Right, that'll work, and that's full credit, right? But do you have a slicker way to combine any of those at all? Well, plus or minus 2 pi n doesn't get us anything because n could be negative or positive here. Maybe we can combine these first two statements somehow. Crystal, you got it?
I mean that maybe it's 0 plus pi n.
Yeah, I think really, isn't this trying to communicate that this is a solution? This is, and so is this, and so is this, and so is this, right? So I think you could just write pi n, right? Is what Crystal's saying. And that captures both of these at once. How about capturing both of these? Could you combine those? How? Yeah, Bruce? plus or minus pi over 4. Well, no, because this is pi over 4, but this is not negative. This is not negative pi over 4, huh? Pi over 4. Yeah, we could maybe write it that way. Right, that's a little more compact way of writing the solutions, right? In fact, so the first one I would consider somewhat of a coincidence, these two first statements here that can be combined into that way. It's not always true that we can do that, that the solutions to an equation of the form sine u equals a number are going to come in that with that frequency. But it is definitely not a coincidence that the solution to this second equation, tan u equals a thing, that those will be able to be written in this compact way. Tell me why. You maybe expect them to repeat this often. What do we know about from the last unit about the tangent function? Yeah. Yeah, so we kind of expect that if you ask me tan u equals something, that the solutions I give you will be periodic with period pi, right? So that's not a coincidence at all. In fact, every time you encounter a function, a little problem at the end with that form, you'll be able to write it that way. Okay. Lauren, did you have a comment? No? Sorry, I kept ignoring you. My apologies. Okay. I'm sure it was good. Let's do it again. Solve for x again.
But this
What do
is
you-
just. Oh, wait. Is this like all of the values?
Yeah. Maybe we say that. I don't know. And then, you're welcome. And then
Oh, this is simple.
cosine x equals plus or minus a half. So this is nice, right? What does x equal? Well, it equals anytime cosine is a half or negative a half. So that's like all of the all four quadrants with the over 3's, right? So like pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3 all work. But again, as usual, here, as what we've been doing recently, at least, we want to write the solution for all values. So how can we do that? Can you do that in the slickest way possible, please? I want to come see what you come up with. One way to do it would be just write pi over 3 plus 2 pi n, 2 pi over 3 plus 2 pi n, 4 pi over 3 plus 5 pi over 3.
Would you write like pi over pi over pi over
Wait, so you can just write
Come on with a slick way to write it.
Wait.
All right, we're running short of time. Here's, I think, the best way to write it. Are you ready?
Yes, sir.
Here's the.
What was that? Like, what was that voice?
Caffeine with the Swedish
Is that a nice way to compactly write it?
Yes, I kind of.
So pi over 3, or anything, right? Pi over 3, or this, or this, or this. That's what happens if that's positive. If it's negative, we're catching all of these, right?
Good job. Another one?
We gotta do one more before you. Yeah, we do. We got a minute.
I keep thinking that you're the last one.
I actually have like a ton more slides. Actually, my goal is to like show you as many examples as possible. What do you want to do? Don't you want to factor it? Me too.
Oh wait, this was finally one where.
Wishful thinking, maybe that's a 5 and a 1. Wishful thinking for the win. Okay, good, that works. All right. So cosine is either negative a half. I feel like we've done that one before. Or cosine is negative 5. I don't know what that is. We'll figure it out in a second. So that's 2 pi over 3 and 4 pi over 3. By the way, thankfully we're back here on 0 to 2 pi. And now we just need to figure out when does theta give us a value that cosine of that angle is negative 5. When is the cosine of an angle negative 5? Maybe we need our calculator for that. I don't know what that angle is. Wait, what? At a non-existent angle? Yeah, there's no real value for theta that makes that true.
Yeah,
Right?
I was like,
Can cosine ever be less than negative 1? I don't think so. Only 2 answers there. Have fun with
oh my
homework.
God, that was such good timing.
Homework 4 tonight.
Okay, you know what?
I know you'll love it.
Something back here.